Hello everybody and welcome back. Today we're going to look at a medium rated problem for which the brute force solution is quite easy and we'll discuss that. But things get a little bit more complicated if we want to optimize the solution. In fact, the brute force solution runs in order of n square time, but we can reduce it to order of n time. Now the optimization is so crazy that it brings down the runtime from 2000 milliseconds plus all the way down to close to 40 milliseconds. Now the difference is quite crazy and so is the optimization. Anyways, enough talking, let's get started with the solution to the problem, path sum 3. The first thing I like to clear up right away while solving a question is to know what kind of input outputs we're dealing with. Now in this question we're given two pieces of input. One of them is target, which could be an integer like 8, and the other is the root, which is the root of the tree. Now this tree could be something like shown below. The goal of this problem is to count the number of paths which have this target as 8. Basically, to explain and show, one of these paths could be something like this, where we're basically doing -3 plus 11, which is equals to 8, the target. And this is why we do paths plus equals to 1. Another possible path is considering this 5 to 1 over here, which also sums up to 8. So we'll do plus 1 again. Similarly, we have another path 5, 3 over here, giving us a total of 3 total paths that follow this target condition. Pretty simple in terms of setup. Now we'll want to jump into the brute force approach for this solution. As I suggest, it's always a good idea to look at the brute force solution, figure out the bare minimum thing that works out, and try to implement that. Maybe in doing that, we can figure out more sort of key insight and nuances in the problem that can get us closer to the optimized solution. First, let's implement the brute force solution. As we saw previously, we want to somehow calculate the sum of the paths. And one way to do that is just by using a DFS. So we'll use a vanilla DFS, taking the input as the node. But we also want to keep a track of what is the current sum up till now, so that we can maybe figure out, okay, if this sum is equal to the target sum or not. So we'll also pass in the current sum. Now I like to start off DFS by writing this base condition, if not node, return 0. Basically saying that if we are at a null node, a none node will return 0. Let's not go any further. Okay, with the base case out of the way, what do we do now? The goal of this problem is to go in these right and left directions and try and find which of these paths works out the best. So what we'll do is, I'm going to run a DFS from the node and we'll go to the left node. And now I'm going to pass the current value. This current value is no longer the current we saw before, but increased to the current node's value. Basically, we are coming from some point, we'll look at the current node value, we'll add it as the current value and send it to our children. This is just sort of accumulating the sums that we're seeing. I'm going to call this DFS with node.left. I'm going to do the same for node.right. As simple as that. Now we also note that the entire goal of this problem is to return some count, some path count, that is what we're looking for, some count. So we'll do count plus equals to there. Basically go to the left and right children and increase the count to whatever they give. This count will also have to initialize to 0 over here and we'll return this at the end. So this sort of is sandwiched between this initialization and the return. Things would have been fine, but if you realize we aren't really checking for the target up till now, we also have to implement that check. So I want to say if the current sum up till now, the cumulative sum up till now is the same as the target sum, if that is the same as target sum, then hey, great. Great, we've found a match, which means that the current path we're looking at, the current path up till now, at this particular point of time, is a valid path. It is a path that gave us the current sum as the target sum. So this means we're able to count plus equals to 1. Again, life would have been simple if it were that easy. However, there's one more condition that we want to look at from the question itself. Let's focus on this line. The path does not need to start or end at root or leaf. What this says is, what is the assumption here, by the way? The assumption is that we're starting the DFS from the root, setting the current counter to be 0. And that was the initial assumption. We're starting from the root we're starting from the root with the count as 0. But this condition says that, you know what, it's not always the case that you want to start from the root. There can be other possible paths which are not starting from the root. Take, for example, all of the cases in this case. This particular sort of structure is not starting from the root. It's starting from this node -3 over here. So we have to somehow have the ability of skipping over nodes. Saying that, you know what, I don't like this node. Maybe it's time to reset the counter back to 0. What we'll do is we're just going to copy paste this guy or put it over here and say that instead of starting from the current, which is what I have been given up till now, like this is the current cumulative score that my parents have given, I want to start afresh. I want to start from 0. So let's do that. So great. We are very close to writing the complete brute force solution, but there is one more thing I want to show you. There is one small issue though. And let's take an example like this one where x is the root, y is a child of it, and z is a child of y. Let's consider this kind of very basic structure and we'll try to see what is happening. Let's say that we are starting off from x. So before it, the current was 0. After we've considered x, we'll pass on the current as x, which is basically 0 plus x. So this is what we send to y. Now y is okay, fine. I got the current as 0 plus x. I am myself going to send the current as 0 plus x plus y. So whatever it got previously and y added to it. Pretty simple. Now let's say that it comes to z. Now z is a bit unsatisfied with its parent and says that, you know what, you all gave me this x plus y thing. I'm not satisfied with this and I'm going to draw boundary. And I am going to restart this current counter back from 0 and do my own thing. I'm going to pass my own current equals to z to my own children. So it's sort of considering this tree right now. As we saw, it's a perfectly valid thing to do. Right? We have this, the path does not need to start or end at the root. So z says that, you know what, I'm not the root, but I still want to be able to start from current equals to 0. So I will do that. Now this is one possible case where we have considered this green subtree. Okay, we've considered this subtree and we'll keep that in mind. This subtree starts from the current of 0. Okay, let's clean this up and we'll do one more thing. See, earlier we started from current equals to 0 and considered x as the grandparent. Instead of that, let's go ahead and consider y. Because see, what can happen is y can also become unsatisfied with its parents. Y can say that, you know what, let me go ahead and draw boundary. I'm not satisfied with the current equals to x that you gave. I'm going to start my own current equals to 0 and I'm going to send my children current equals to y. Again, this is also fine, and when z times comes, it's going to give current equals to y plus z instead of x plus y plus z, because we requested a reset at this particular line over here. Perfectly valid thing to do. But let's say that z again becomes unsatisfied. It draws this second boundary, second time, and says that, you know what, I'm again going to start from current equals to 0. Perfectly valid thing to do again. But if you realize, if it's going to start from current equals to 0, it is going to be the root of this subtree, and whatever computations it is going to do right now are going to be the exact same when we started off with x. One case was we started off with x and z requested a reset. And the other case was we started from x, went to y requested a reset, and then z requested a reset. Both of these cases at this point of time are undistinguishable from each other. What it means is z is going to be computed twice. And we don't want that. We don't want recomputation, because that means that it would be counted twice. So we'll have to do a quick check to see if this reset is being done properly. Now, of course, we can't do directly 0. We'll have to include one more thing. We'll include one more parameter saying whether the current guy has been resetted or not. So we'll call it a reset, and we'll call it from 1 over here, saying that we started off from root node and root node itself was a reset. Okay, now we're going to do is we're going to say if you requested a reset, if this current node requested a reset and this node is already in a resetted list, in that case, return 0. We'll also create this resetted list, which we are going to call it a set because there can be repetitions and we don't want that. So we'll say if reset and node in resetted, basically if you requested a reset and you happen to be inside of this resetted list, which means you've already requested a reset before, you wanted to start your own thing, you want to start from count 0. If that is the case, return early. We've already considered you, will not consider you again. In the other case, if you still have requested a reset and you are not inside of this already considered, well, we'll go ahead and consider you for now. So we'll do resetted.add this current node and we'll pass on with our computations normally. Okay, this basically marks the end of our solution for the brute force part. Let's do a quick sanity check and I'm going to show you the very bad runtime it's going to get us. Okay, so this time it gives us 1660 milliseconds, but there is an optimization that exists, which is so beautiful, which is so powerful that it can bring it down to less than 50 milliseconds. Just a quick by the way, if you're still not clear and you want another sort of take at it with a more detailed analysis of what's going on with every single thing I explained again, I'll link to this blog down below, which I have myself written, and I tell you exactly what has happened, and this should give you another sort of perspective into the same problem. Again, everything included, code and complexity analysis, as well as the optimization that we're going to talk about. Before we dive into coding the optimization, I want you to focus on this one line. Line number 16, which says that current plus equals to node.value. What it is essentially doing is it's accumulating all of the things that it gotten from its parent. Now this cumulative thing is very interesting. In fact, let's dive into this in a bit more detail and we can finally figure out something that is going to help us in the optimization. Okay, let's take the case of, let's just say that instead of, looking at this 2D tree, let's just boil things down to one-dimensional array. I'm going to pick the array elements as 10, 5, 3, 3. Okay, very simple, just the left branch elements. So I'm going to specify this nums equals to 10, 5, 3, 3 as an array. Let's say that my temporary goal is to now query elements and say that get me the sum of all the elements from I and j, where I and j is being specified by me. So let's say that one of the queries I can give is get me the sum from 0 to 2. What is the one possible way you can do? You can look at 0, okay, it's 10. You can look at 1, you can say it's 5, and you can look at it's 3. So this is going to give you a sum of 18. So you can return 18 as the answer. Similarly, when you are looking at a case like say 0, 1, you'll go to 10 and you'll add 5 to it, giving you 15. Similarly, if you do 2, 3, you'll do 3 plus 3, pretty simple, 6, and so on and so forth. Now I bet some of you have already looked at the next cat videos that have lined up, but I know this is cumbersome and we want to simplify this. See, the thing is, what we're trying to do is we're trying to take the sum of elements from I to j, from I somewhere around here to j somewhere around here. And what this is essentially doing is it's doing an order of n operation. It's iterating from all the elements I all the way up till j and taking the sum of all of these. But we can make this query more efficient. Instead of replying in order of n time, we can reply in order of 1 time. How? We're going to take something called cumulative sum. So we'll start up the cumulative sum from 0. And this is sort of the general logic behind the cumulative sum. I'm going to take this 0, I'm going to look at 10, and I'm going to add 0 to 10, which will give me 10. 10 will look at 5, add it to itself, and it will get me 15. Similarly, 15, 3, 18, and 18, 3, 21. This is just cumulative sum of the array. Let's relabel them as 0, 1, 2, 3, 4. And this time, instead of doing it in order of n as we had before, we took order of n time to answer and reply, we can do it in order of 1. We can return a solution in order of 1 time, saying that cumulative of j plus 1 minus cumulative of I is going to get you the answer. Okay, let's quickly verify it. Let's say that again I have the query of 0 to 2. What is it going to give me? So I want to access the cumulative 3 minus the cumulative of, so cumulative of 3 is 18 and the cumulative of I is, which is 0, is going to be 0. So the answer is 18. Let's quickly verify it. So 0, 1, 2. These are all of the 3 elements. So 10 plus 5 plus 3. Cool. This works out. It looks like it's the correct logic. We can again do it for 0, 3. Again, we can do this in order of 1 time instead of order of n as we had before. So 0 to 3 is basically array of element 4 minus the array of element 0, which is 21. Again, you can feel free to verify this. And we can do this on, and each of these queries will now, instead of taking order of n time, will take order of 1. This cumulative something is very, very interesting, and this holds the key to our optimization. Okay, it's finally time to bring this back from 1-dimensional back to 2 dimensions, and we'll see how we can think about that. Now let's start calculating the cumulative values for this particular tree. We're starting off with 0 and we have 10 over here, so we'll write 10. If we go to the right hand side, 10 plus minus 3 will become minus 7. Minus 7 plus, plus 7. Plus 7 will become 18 over here. Fine. Similarly, if we go on to the left hand side, we have 10 plus 5. This 15 goes here, which is 18. And this can go over here, which is 21. So we'll keep that in mind. Similarly, if we want to go to this side now, we have 16. Similarly, we can write this for these and these guys. Now, there's something that's happening, something very, very interesting. See, previously, what we were trying to do is we were trying to subtract both of these cumulative sums to get the sum of this query, right? Mathematically speaking, we were doing a cumulative of some future value minus cumulative of some past value, and you were getting the sum. In this question, things are a slight bit rearranged. See, instead of you looking at future, past and getting me the sum as the answer, I'm giving you sum as the input. Sum is an input. And let's say that we also have the information of what the cumulative of past is. Can you figure out what the cumulative of future should be? You can just rearrange and write it this way. We'll do it this, and we can do this. Pretty simple, pretty basic math. But there's something that we want to focus on. Look at this 10 over here. Assume that this is the past. Our goal, our sum is the target over here, 8. So when I do 10 plus 8, I am sort of in a way looking for all of the values that are 18. All of the values that are 18. Where are all of the values that are 18? One of them is here, one of them is here, and one of them is here. Things will start to fall in places now. What's happening is, starting from this node, I'm going to look at its left and right children. And let me get rid of this because only 18 is the important part over here. I'm looking for the value 18. And what I'm going to do is I'm going to explore in the right and left directions. And I'm going to ask, hey, assuming my past is 10, can you get me the score of 18? Assuming my past is 10, can you get me the future of 18? And so we can look at this particular path over here, which ends at 18. So this is one possible answer. Similarly, when we go on to the left hand side, we are looking at this 15 over here. That's fine, we don't care. And then we have 18. So we have this 18 over here. Great. We have one more path that we can mark. Because this ends in 18, we can end it right here. Similarly, when we move on from this place, we can also realize there's one more path hidden like this. And in this way, we were able to find 3 total paths that had ending as 18 and the starting as 10. What does that mean? We were looking for a target of 8. We were looking for a target of 8 and we found the start as 10. And this is what we are looking for into the future. If any of its children, if any children of 10 can get me the score of 18, then I will be happy and satisfied. Okay, I want to take one more example because this can seem like too much of good luck that we have struck. So let's take one more example and try to see what happens then. Let's say that instead my target was 6. This will bring forward some very important points, okay? Now we'll start from this 10 again. And we want to start go ahead and exploring in both of these directions. Now since the target is 6 and the current value is 10, I'm looking for a value that is 16. So I'm going to look at this guy over here. I'm going to go to the left first. So let's go to the left. We'll see 15. Okay, I don't care. 17 over here, 18 over here, nothing too good. Let's go back. We have 18 over here, 21 over here, nothing good. Let's go back and we have 16. Hey, great. We were looking for 16, right? This means that this entire chain, let me just clean this up. This entire chain, oh, not including that, damn it. Just this part where we are starting from is not being counted, okay? We're just taking the node dot left of it. So it's 5 plus 3 plus minus 2, which is 6. Okay, this is fine. This was assuming 10 as the root, but maybe 10 isn't the root. Maybe there is something else going on. So let's say that this is the root now. Instead of 10, I'm going to make 5 as the root. Now, what is the target going to be? Well, we have the value 15 over here. So we'll do 15 plus the old target. And I'm looking for the value 21. Now let's go ahead and explore in the left direction. 18, no. 21, yes. So this is one possible answer. And if you see, this indeed adds up to 6. Okay, if we go in this direction, we don't have anything. That's fine. We can go here. No 21 yet. No 21 yet. So there is only one possible more answer for this particular subtree. So there is only one answer we found out, which is this. And we found another. So this one came from this guy and this one came from this guy. And in this way, we are sort of having this structure where we can look at the target, we can look at the cumulative sum, assume this to be the root and try to figure out what's happening. This may be a bit confusing because it is a slight bit complicated question, but I think the code should make it more clear. So let's jump into the code. Okay, ladies and gentlemen, we have finally reached the end and we'll start to code up the optimization. The first thing I want to bring your attention to is this line number 13, which is current plus equals to node.value. As I said before, this is the most important line and we'll keep that intact from our previous solution. I've cleared up most of the rest of the things. Okay, because we have this cumulative thing and we are not messing with resetting these values anymore, we can just do node.left and call it with the cumulative current sum. We'll do the same for node.right. Now the thing is, we can send these children from the node.left, node.right, and we can go ahead and accumulate all of this cumulative sum. But the thing is, we also want to be able to store values like 15 and 21. And that's because let's say that we are at this current point 15. We have the cumulative current sum as 15. At this point of time, I want to be able to set a goal, a target for our search to somehow figure out 15 plus 6 in the tree. That is, when I'm at this point 15, I want to do 15 plus target. I'm going to do current plus target, and I'm going to set that as my goal. This is the value I'm looking for. So if any of you, both of you searches can return me this goal somehow, then I will be happy. I can somehow increase the answer count by 1. I'll actually go ahead and write this answer equals to 0 over here and we'll increase the, I'll put non-local answer and we'll do answer plus equals to 1 something, if something. Otherwise, we have this goal equals to current plus target. Now, we go back to this cumulative thing. See, when we have this nums array, which is now our tree, like this 1D thing is now two-dimensional for us, we were able to compute this cumulative thing very effectively because we just had to iterate and we just had to count. Now we're still able to count this cumulative sum, but there's one issue. Previously, we could access this cumulative of j plus 1 and cumulative of I to figure out their difference and return the sum query as before. But we no longer have access to this j plus 1 or I. We are no longer in an array. We don't have these indices. We are in a tree data structure. How can we deal with that? One of the possible ways is to say that I'm going to mark the current plus target, which is the goal, and I'm going to mark the goal as 1, saying that somehow I've marked this goal right now, and I'm going to say answer plus equals to 1 if the mark of current, basically I can do just this. Okay, what I'm trying to do here is saying that at some point of time, let's say that we are in the case of 15, this is our current value. So I have this current value as node.value. Okay, current is 15 now, 15 at this step. I'm going to set the goal as 15 plus 6. This is my target, goal plus target. So goal is 21. I basically marked the value of goal, marked the value 21 to be 1. I'm saying that this is the goal I want to reach. Now I'm going to go ahead and explore in the left and right children, and hopefully sometime later in the iteration, sometime in the future, I can get to this value, which is mark of current. Now the current value in the future can be 21. And if it is 21, I've already previously marked it as 1. And in this way, I can sort of set goals for my future recursion to check. Amazing, right? This is so like mind blowing. Anyways, once I've set this goal, I should also be able to remove this goal. And I'm going to remove this goal over here. And why do we want to remove this goal? That's because let's say that you were at this point 15 and you explored both left and right children and you were able to increase the answer by some amount. That's fine. Everything worked out great. But at the same time, we want to be able to set this mark of goal 0, because when we are at this point, when we return from this node back to the root node, I want to again start considering the left and right children's answers. And at this point of time, the current is 10. So I can no longer set the target as 15 plus 6, which is 21. I have to somehow reset my goal. I have to reset my target to be 10 plus 6. I have to reset my target to be 16. This is fine, right? Okay, let's also initialize this mark. We'll call it a default dict, and this will have integer values. This is also fine. We also want this non-local mark to be there. And instead of doing this, I'm going to return this answer. And here we're going to return nothing. So the structural change that we did is that DFS is no longer returning the count. It's no longer returning the answer. The answer is something we're going to store separately. And we're going to deal with that by increasing or setting the goals and then checking if the mark of current is 0 or 1. Pretty simple. But there's an issue. Even if you run these on sample test cases, okay, we'll fix that. What is the target? Okay, it's the target sum, my bad. Okay, fine. So we can finally have these run. Wait, why wrong answer? Okay, so there are two more things that we want to set up. First is that the mark of 0, the mark of target sum should be equals to 1. Why is that? That's because you can think about it this way. This is sort of setting up the base case as like the cumulative of 0 is 0. This is something of that sort. Cool. So now we have accepted in both of the cases. Now, before we get too excited and run this, there is one more thing I want to show you. This is like I promise this is the final thing, okay? Let's take a very simple case like 0, 1, 1. That's fine. And we'll set the target as 1. In this case, what do you expect the answer to be? We can have 1 over here, 1 over here, this over here, and this over here. There are a total of 4 cases that we can have, and that is the correct answer. But let's look at what would happen following our own logic. The first thing we'll write down is the cumulative sums. So 0, 1 and 1. Pretty simple. Now, I'm going to go ahead and look at this 0. Okay, I'm assuming this 0 as my root. Now, when I assume this 0 as my root, what is the goal going to be? It's going to be 0 plus the target. So the goal is 1. And I'm going to set the mark of goal, the mark of 1 equals to 1. In this way, I've set this target, I've set this goal, and I will go further into the tree and try to find this 1 over somewhere. Now let's say I go to the left node and I'll go ahead and look at its value. Okay, great. 1 matches with the 1. So we'll have the answer as 1 over here. That's great. Okay. What if I go in the other direction? What if I go this way? I'll also go ahead and check this value and it looks like it's the same as 1. So that's great again. Now I have the value of 2 over here as the answer. Now we're going to go ahead and return 2 as the final answer for this case. So what are the cases we have marked? We have looked at this and this. But what this does not consider, and this by the way would be the completion of our entire algorithm, like this is it. What we haven't considered are 2 of these other cases. Both of these cases including 0. And that is because we have set the mark of 1 equals to 1. When instead we should have been doing mark of 1 plus equals to 1. Because just doing this plus equals to 1 will allow us to consider both of these 2 more cases coming from 2 of its children. This gave us the answer of 1. This gave us the answer of 1. And so when this 0 comes, it will look at this one and add 1 to itself. So it will look at the previous one, add 1 to it. Similarly for this case, it will look at this one, add 1 to it. This can be a bit hard to, so feel free to write it down yourself. But what we're essentially going to do is this simple change. Just add plus over here. Similarly, instead of setting it to 0, we'll do minus equals to 1. We're finally done, so we can go ahead and submit this. And we get a runtime of 44 milliseconds. Anyways, yeah, so this is the long detailed explanation of the problem, part sum 3. If you like this video, if you appreciate my efforts, give it a thumbs up. If you don't like it, give it a double thumbs down. It really lets me know. And if you want to see more of these high quality detailed explanations of LeetCode problems, subscribe. And as always, thank you so much for watching.